It is with great pleasure that I can welcome you to the Storer Lecture Series and being given by Professor Simon Levin. I first met Simon 36 years ago, and he remembered the details better than I did, because I said that it had to do with the elections in New York State at that time, and he can tell you later. This is somebody that in some sense truly needs no introduction. Also, for people walking in late, there's about 10 seats up front in the first row. So he's someone who truly needs no introduction and has asked to be short. I mean, I could spend the whole hour giving his honors and then leave him no time to talk. So let me simply say that he's recently won numerous prizes, which are mentioned on the sheet, including the Kyoto Prize, which is very prestigious, the Heineken Prize. He's a member of the National Academy of Sciences and all sorts of other wonderful things. He's now the George M. Moffett Professor of Biology at Princeton University, and the title of his talk today is right there, Learning to Live in the Global Commons. With great pleasure, Simon.
Thank you very much. I have to turn this on. Right? I'm completely mic'd up. Okay. Thanks very much, Alan, for the introduction. It's always a pleasure to be back here, and especially to see Alan, who was one of my first and best ever graduate students, and he seems to be doing okay. So I thank you all for coming. I'm going to talk about some evolutionary aspects of ecology. This represents, but I'm going to be talking not about the classical aspects of evolution, but about the evolution of the subject, and in a way the evolution of some of my interests will come in too. So the history of ecology, which of course is embedded in the insights of Charles Darwin, is also a history of a subject that's been in evolution. Darwin's voyage of the beetle really transformed our views of nature, and its origins were in natural history, the work of people like Forbes, Clement, and Gleason, and natural history remains the foundation of the subject. But understanding ecological patterns meant understanding dynamics. So early in its history, ecology embraced mathematics, great mathematician Vito Volterra and Alfred Lotka, and the subject evolved through partnerships with mathematics. And in so doing, it was really rediscovering insights that were old. It went back to the 17th century to the work of demographers like John Grount, and even earlier to Fibonacci, Leonardo da Pisa, who built one of the first, demographic models. Grount's work was concerned with understanding the demography, for example, of London by categorizing the rates of birth and death, and in particular the causes of death. Here you can see it a little bit closer up. This is a now famous slide of something which sits in the Guildhall Museum Library. And if you look at some of the big causes of death there, lethargy was one of them. There's some that I won't even discuss on there, like overlaid, and suddenly was a cause of 2 deaths. I thought the next one was a surfer, but I guess it's surfeit. One person died having thrown himself out of a window being distracted at St. Clement's Eastcheap, and 29 people actually died from teeth. But it doesn't say whose. So as ecology matured, it went beyond this. It found linkages other places in evolutionary biology, of course, with the mathematical development of that subject, and in the physical sciences, where there were many insights for understanding ecological phenomena and continue to this day. The focus in later years shifted to understanding biogeochemical linkages and patterns at the level of whole ecosystems, such as the studies at Hubbard Brook Experimental Forest. And partnerships also developed with engineering, both in the understanding of ecological phenomena and in providing pathways to their solutions. And in recent years, obviously molecular biology has brought fantastic new tools to ecology. And these have opened up possibilities that, as Jonathan Eisen knows, have occurred faster than we can actually plan for their use, but great opportunities. But all of these advances aren't going to lead to solution unless we deal adequately with the human component. I'm going to argue today, and all of my lecture is going to be about what I consider to be the newest frontier. It's not brand new, but it's in building bridges with economics and the social sciences, with people like Kenneth Arrow, the great Nobel laureate in economics, and Lynn Ostrom, who's worked on solutions to problems of the commons, and Partha Dasgupta, whose concerns have been with poverty and wealth and social capital. This is the human footprint on our world, and it threatens our survival, and therefore I think it demands our attention. And this obviously raises challenges that are both ecological and economic. Things like, how do you value biological diversity? There's a lot of concern about biological diversity and the loss of diversity, but are all aspects of biodiversity the same? How do we put a value on that diversity? How do we value the services ecosystems are provided? What is it that makes ecosystems robust and what therefore makes them fragile? And how would we know when we're on the verge of losing some of these services? How do we deal with problems of discounting, meaning how do we value present use against future generations? And how do we deal with not only intergenerational equity, but also intragenerational equity? And most importantly, perhaps for the problems I'm going to talk about today, how do we achieve cooperation in dealing with problems of the commons, and what can we learn from evolutionary theory about how evolution has dealt with problems of cooperation? So all of these issues have both economic and sociological dimensions, and all of them have both ecological and evolutionary dimensions. And nonetheless, ecology and economics often have been viewed as antagonistic disciplines at odds with each other, but I'm going to argue that that's wrong, at least that they shouldn't be viewed that way, that ecologists and economists have lots of incentive for interaction. And there are two basic reasons for that. One is because ecological systems are embedded in a socioeconomic framework, and the linkages between ecological and social and economic systems are really key to achieving environmental protection as well as economic growth. But there's another reason ecologists and economists have lots of incentives for interaction. This is a feeding frenzy, which could be just a bunch of animals, but these are investors. So the same sorts of phenomena occur in both systems. Ecological and economic systems are alike, and that's not just accidental. Economic systems are, in fact, special cases of ecological systems with exploitation and cooperation and parasitism, or you can view it the other way around if you prefer, which is that ecological systems are economic systems because there's competition for resources, there's specialization of function, etc. And most fundamentally, ecological and economic systems, ecological and socioeconomic systems are what have come to be called complex adaptive systems. That's perhaps not the greatest term because it implies that these systems adapt and they'll take care of themselves, but what it means is that they're systems made up of lots of individual components, and that those individual components, individual agents, for example, adapt and change, and that the systems change, and they change at many different levels, and many of the macroscopic changes are the result of decisions that individuals are making, and that therefore one has to integrate phenomena that are going on multiple scales at the same time. And systems of this sort, large-scale phenomena, are emergent from the collective behavior of individual agents. And when that's the case, those patterns, those collective phenomena feed back to influence individual behavior. This is, unfortunately, the problem we're facing when we're dealing with global environmental problems. It's why we're facing such serious ones, because we live in a global commons. And in a global commons in which individual agents are acting largely in their own self-interest, and that the social costs are not being adequately accounted for. That's not just an ecologist speaking. Economists have come to similar conclusions. And it's true even when the individual agents are not people, but nations like ours, who are players in a global commons game, but have to balance what they perceive to be the interest of the group against the interest of the greater good. And these don't always play out the way we'd like them to. So this is how we're viewed in some of the world's press because of that. Well, problems of the commons are widespread. They include, as you've been reading a great deal about recently, problems of fisheries and their demise because we're all fishing out of a common pool, aquifers that we share. Commons problems don't mean just that we take things out, but we put things in. This says I keep thinking about all those black holes going to waste, somewhere to put one's pollution. Vaccine usage is a problem of the commons because at some point the benefits to you from getting your child vaccinated, the benefits to your child, are probably there's probably not a net benefit under some circumstances, but if everybody felt that way, it's in the same way as if nobody went to vote, then there'd be a collective problem. So there is a problem of the individual benefit cost calculation versus that of the group. Antibiotic use, we know about, is a major commons problem. Antibiotic resistance is on the rise. This just shows you what's happened in the last 15 years with ciprofloxacin resistance, and there are lots of other examples of the rise of resistance to antibiotics. Part of the problem is that hospitals are commons. What this slide shows you is the level of antibiotic-resistant bacteria, methicillin-resistant and vancomycin-resistant in hospitals as a function of how many days patients have been in the hospital. And what you see is patients generally are sick when they come to hospitals. That's why they go there. But they get better if they're there a few days. But if they've been there a long time, their levels of antibiotic-resistant bacteria tend to go way back up again. Now, maybe some of those are in there because they've got high levels, but it also means they've acquired many of these in the hospital situation. So the hospital is a commons in which we acquire these. There are many efforts going on now in this country and elsewhere to restrict the use of antibiotics, to encourage people not to use them under circumstances that are not required. But what would you do if your child has an ear infection? How much will you take into account the common good in deciding whether you ought to give that child antibiotics? Now, there may be other reasons the child shouldn't get antibiotics, but most parents will not take the collective good into much account, and probably shouldn't, because it's a very small term in the equation in making decisions. So dealing with the commons means that we really have to deal with the dynamics of collective phenomena. I have to thank my former postdoc, Ian Cousin, for these movies which he made with the help of the BBC. I'll come back to talk about these phenomena in a few minutes. But these are collective phenomena, and this dealing with collective phenomena is a deep challenge, and it's one that's been faced in many branches of science for a long time. The core problem is the tragedy of the commons, which is usually associated with Garrett Hardin, but it really goes back, as Hardin acknowledged, to William Forster Lloyd, who wrote, citing what happened to the pasture lands, well, this is Hardin talking, left open to many herds of cattle. Lloyd pointed out that with a resource available to all, the greediest herdsmen would gain for a while, but mutual ruin was just around the corner. So Hardin then wrote, so must it be also, I realize with growing human populations when there's a limit to available resources. It was so in Lloyd's day, it's even more so today. And that was some years ago, so it's even more so today than it was then. The challenge of the commons is dealing with public goods. And the solution, according to Hardin, was mutual coercion, mutually agreed upon. The question is, how do we get there, or can we get there? How does cooperation arise in nature? So let me just take a short detour here, and in particular, does mutual coercion, mutually agreed upon, also arise? Well, altruism was a puzzle even for Darwin, in particular in the haplodiploid insects, to which I'll explain for those who don't know what haplodiploid means in just a minute, in which the bees, the ants, the wasps, in which the females often give up their own fitness in order to help their sisters. And Darwin at first was puzzled by that, but later he came back to some explanations. But the real explanation was given first, I think, by J.B.S. Haldane, who said that, in an offhand comment, that he would lay down his life for two brothers, two siblings, or, he said, for 8 cousins. He never actually did that, but he was taking into account his degree of relatedness to his siblings by essentially 50%, to his cousins by 1/8, 12.5%. The theory was developed, as many of you will know, much more deeply mathematically by the late W.D. Hamilton, working with the haplodiploid insects. So the haplodiploid insects are those in which the males arise from unfertilized eggs, and therefore the only genetic information they get is from the mother. And therefore two females who have the same father are inheriting the same genes from their father, and 50% of the genes from their mother, so they share 3/4 of their genes, unlike Haldane and his sister, who shared 50% of their genes. So there's a much higher genetic relatedness, and Hamilton worked out the mathematics and showed how this could facilitate the evolution of what was called altruism, because an individual could get more of her genes into the next generation by helping her sister than by trying to go it alone. But close genetic relatedness is not the whole story. It's only part of the story. We get cooperation among unrelated individuals simply through what's called reciprocal altruism. You scratch my back and I'll scratch yours. And one doesn't even need that. One can simply have repeated interactions among unrelated individuals. I was talking to Pete Richardson earlier about the work of Ernst Fehr. One of the experiments of Fehr's that I'd like to quote is one in which he shows how punishment can emerge, and punishment becomes a social norm for individuals who are engaging in asocial or antisocial behavior. In particular, in this experiment, he had essentially 100 individuals, each of whom had a certain amount of resources that they could spend each generation. They could spend them on themselves, they could spend them charitably helping others, or giving them to others, or they could spend them punishing others. And everybody knew at the end of each generation what everybody else had done. And over time, charitable behavior increased. Individuals started out being very selfish, but charitable behavior increased, and individuals spent more of their resources, even at cost to themselves, punishing others because they were who they deemed had not been charitable. There were a small subset who actually punished people who had been charitable, but that's what makes life interesting. We learned from this and other experiments that humans will actually spend their own resources to punish others who deviate from social norms at cost to themselves. And in fact, punishment itself is a norm. I don't know what the rules are here, but I know at Cornell and Princeton we have honor systems. You have to follow the honor system, and if you see somebody who violates it, you're also required as part of it to report them. So punishment itself becomes a social norm that is expected to be maintained. More generally, the localizing of interactions can also favor cooperation, and thus summarizing this part, tightening feedback loops, whether it's through a genetic payoff or through reciprocal altruism or through tight spatial localization, can enhance cooperation and coexistence. But that's not enough, because those sorts of feedback loops also work for rewarding selfish behavior, such as, for example, allelechemic behavior, allelopathy, in which individuals will poison other individuals in their neighborhoods. So tight feedback loops can also foster greed and selfish behavior, and therefore, in human societies at least, and also we're learning in other animal societies, social norms have emerged to reinforce collectively beneficial behaviors. Now, social norms are a form of collective behavior, and this is for you, Alan. Collective behavior, we see animal aggregations in many animal species. It's a widespread behavior, and a natural question is to ask, how do you move, how do they do that? What's the relationship between an individual agent and how it responds to its neighbors and to its local environment and to the macroscopic properties of ensembles? And what shapes individual behaviors? And how does this have anything to do with human aggregations? And does it have to do with other sorts of behavioral traits than just aggregation, like aggregating around particular kinds of actions and activities that affect our societies? Real aggregations are heterogeneous assemblages of individuals. So I want to talk to you a little bit about some work that I've been doing with Ian Cousin, who was my postdoc, went off to Oxford, and now is coming back joining the faculty at Princeton. And in which we asked the question, how is it that this collective behavior can emerge in heterogeneous assemblages? So I want to talk for a little bit about animal aggregations and then come back at the end to ask whether any of this has anything to do with human societies. So I've been interested for a long time in fish schools and bird swarms and how aggregation takes place and how one can relate those collective phenomena to individual behavior. So in the model with Ian, which is not so different from other models that we and others have looked at, we have a bunch of fish, and each one has some velocity vector that describes what it's doing at a particular point in time, and these rules are updated. And they're updated based on the information that's available to the individual regarding its environment, for example, where it thinks food is, and also in relationship to what other individuals are doing. The model, I should tell you, is a stochastic model, but you're not going to have to think about that a lot. So first of all, one takes into account the distance to other individuals and how many individuals are in a particular neighborhood. And I'm not going to show you the equations, but individuals update their velocity vectors each generation, in part based on what their neighbors are doing, orienting towards perhaps the center of mass of individuals in the neighborhood, or aligning itself with the velocity vectors of individuals in the neighborhood, the latter being more likely. So secondly, individuals, and that's that vector G at the top, have some information about where the food is, where the predator is, what it ought to be doing. And so the question is, should the animal pay attention to what it thinks is the right information, or should it pay attention to what its neighbors are doing, and how does this behavior evolve? My colleague Naomi Leonard is interested in putting robots out into the environment to gather information, having them communicate with each other, and optimizing the information gain. So she's the top-down controller, but here everything's bottom-up. So this is a different sort of organization that arises. It's self-organization. So what we do is that every individual has an updating vector, a social vector, that's the S that's here, and an information vector, G, and the individual updates its velocity vector as some weighted average of those two kinds of information. That weight is on their omega, and every individual has a different neighborhood, and every individual has a different omega. So if omega is small, that means that you don't use your information at all. You just pay attention to the average of the social vector. If omega is very large, then you don't pay attention to the social vector. You're just paying attention to your other information. And in some of the simulations, we allow omega to be adaptive. In other words, if you've made the decision of some pathway you ought to follow, and you see that nobody is following you, nobody agrees with you, you adapt that behavior. That doesn't always work for politicians, but it works for fish populations here. So in this first slide, I'll show you, there are 100 individuals. 99 of them are green. They're all followers, and one is a leader. And that leader wants to go to the upper right. That's the white dot. But it can't get anybody to go with it, and so the group goes nowhere. There's no adaptation here. But if you change, you see gradually it's getting up, but it's very slow. Now if I change that from one informed individual to 5, the 5 get out of front. It looks the same for a while. Those 5 get out on the front, and they manage to lead the whole slug up to the right. And if the 5 becomes 10, then the movement is much more dramatic. It only takes a small number of individuals to lead a group. What this shows you here is groups of different sizes. These are the larger groups here, and this is the proportion of individuals who have information. Everybody who is informed is trying to go in the same direction here. I will modify that in a moment. But what you see is that it doesn't take a very high fraction of individuals. And in fact, if I look at the actual number of individuals, by the time you get to 10 individuals, it doesn't much matter how large the group is. They move fairly effectively. This is a measure of how effectively and rapidly they move towards that target. So again, consider the parallels to human decision making. A very small number of people who think they know where they should be going can lead the whole group there. I don't mean this in any deep way, but there's nothing in the model that says those individuals have the right information. All they have to be is have information and be stubborn. Now, what happens if you have competing preferences? Well, if you have competing preferences, it turns out it depends on, I won't show you the data, but it depends on how different those preferences are. If the preferences are quite similar to each other, individuals will split the difference. So suppose here that 5 individuals want to go here and 5 want to go down here and the other 90 are just followers. Then the group goes right down the middle for a while until it gets further along. When it gets to here, there's a bifurcation, and either the group splits or else everybody goes one way or another, depending on the parameters we put into the model. One of the interesting things in the simulations is that if the group suddenly starts to go up here, there's an increased tendency to come back down here, because the closer you get to your target, the less coordinated the arrows are. If they're all pointing down, then there's a tendency for the group to move down. Think about the political analogy here. What this says, if party A is in power, party B gets its act together and everybody pulls in the same direction. Again, the model doesn't necessarily work when we get outside of animal groups. So what this shows is that a little bit of coupling can achieve a great deal. And here, I want to talk about an experiment of Christian Huygens and actually show you a movie that my colleague and Jonathan's, Tim Buckman, who is a trauma surgeon, head of trauma surgery at Barnes Jewish Hospital, carried out. He was inspired by Huygens' experiment, which I will show you, and carried it out. Again, a few other people have done that as well. The reason Tim is interested in this is because it bothers him that all of his colleagues and trauma surgeons, when they treat a trauma patient, treat one organ at a time and don't take into account that everything is coupled together. So in Huygens' experiment consisted of setting out 5 metronomes. I don't know if you can hear that sound. Just do it. I'll rerun it again here. Okay, so I think I broke it. I'm not sure what happened here. I may have to, good, okay. So I somehow eliminated Tim's picture, but that's okay. So here are 5 metronomes, uncoupled, sitting on a board. The one picks them up and puts them on these 2 Coke cans, I assume. And just all the, what that achieves is it introduces some coupling between them, just a little bit of coupling. Huygens apparently was impressed that that all of his clocks were calibrated with one another. Tiny bit of coupling can achieve a great deal, and a tiny bit of interaction in these systems can lead to great macroscopic effects. So the dynamics of collective phenomena we see are, and this just shows you the network of world trade, are remarkably sensitive to even weak interactions. How much does this kind of herd behavior explain about human societies? And can we translate for these simplistic insights about animal movements to human groups? Now remember Fair's experiments. Humans will punish others who deviate from social norms at cost to themselves. Punishment itself is a norm and can evolve from repeated interactions. There's another phenomenon that will be familiar to many of you called the ultimatum game that I think is an even deeper paradox and in which individuals really appear irrational. That's my colleague Jonathan Cohen, who has done experiments on the ultimatum game. In the ultimatum game, I give Lou Botsford here $100,000 and tell him that there's somebody outside who he doesn't know, whom he'll never meet, whom he'll never see again, that he has to share it with. And that person knows the rules. And Lou has to decide how much to give that person. The rules are that the person outside knows what the deal is and either accepts it or not. So how much does Lou offer the person? Well, one argument says offer $1, offer $10, because that person is going to be placed with a decision as to either to accept the money or to reject it. If the person outside rejects it, he gets nothing, but then again, Lou gets nothing. But if he accepts it, he gets whatever he gets. So I play this game in my class, and some people say they would accept $1. But one student said that he would offer 30,000 of the 70,000 to another student, and she said that she would reject that. I said, it will cost you $30,000 to reject it. She said, yes, but it will cost him $70,000. So people have a well-developed sense of fairness, and I think we all have been in situations like this. It's just a question of where what our price is. Many people will simply say, well, they'll give 50%, which is based on a notion that 50% is fair. But it's quite common that the answer is somewhere around 30%, because nobody should turn down $30,000. And obviously, it depends on the culture and it depends on the total amount. But the question is, why do people do this? Why do they engage in these activities that frustrate economists because it's so obviously irrational in that situation? It's obviously because it's important to them to sustain some social norms within their societies. As I pointed out to someone earlier today, if you go in to buy a car and you expect to pay $20,000 for it, and the bill comes and it's $20,005, you'll just pay it and think that's exactly what you expected. But if you go in to buy a cup of coffee and you think it's going to be $1 and it's $6, you'll be offended. You'll think that you've been cheated. And we've evolved these rules of thumb that tell us how to behave in particular situations. So in the ultimatum game, interactions are not repeated, and I think that the behavior can only be understood in an even broader context of understanding how social norms arise. So what does all this mean for addressing environmental challenges? Well, ecologists are well aware of something called Liebig's law of the minimum, which says that the growth rate of species is controlled by the nutrient that's in shortest supply relative to the needs. So I have my own Liebig's law of the minimum when applied to global environmental challenges, and that is that our ability to solve the environmental problems obviously are limited by scientific knowledge, but scientific knowledge is not the primary limiting factor. We know in most cases what we ought to be doing, but rather the limitations involve the willingness of people and governments to accept what science tells us and to make commitments to the common good. So therefore, we need to understand how it is that individuals make decisions, how it is that collective opinions shift. I've argued that changes in social norms are important, and economists have come back and said, no, you can't get those changes unless there are laws and regulations coming from the top down. But my retort is you can't get those laws and regulations unless the social climate is right for those change. Even if you're Al Gore, you don't push for ratification of the Kyoto Accords if you think that you can't get it through Senate. Even if you think that carbon taxes are what's needed, you can't introduce it unless the social context has changed, as it did for cigarette smoking in public places, that makes such regulations possible. So I think our primary challenges are dealing with problems of the global commons, understanding cooperation and punishment and how they arise, and the emergence of social norms. Social norms like foot binding in China, practices that were widespread, that were sustained for long periods of time, that were costly to the individual outside of the social context, but placed within the social context became sustained through effectively punishment. Social norms are often good. Charitable giving is a social norm. And understanding the kind of social norm it is, I think, is important. When experiments are done to see how generous people are, and they're told, for example, that there's a lake that they can protect, how much would they like to give to that? Let's say they'll say $100. And then in parallel studies, there are 10 lakes that could be protected. How much would they give to that? The answer is $100. People have translated this as an obligation for themselves. They decide how much they should give to this particular cause. It's what's called the warm fuzzy feeling. And they disconnect their actions with the consequences of their giving. So charitable giving is another case where we have translated a social good into individual rules. How do systems of justice arise? Moral persuasion, these are all things which are in the common good, but then we have caste systems and overconsumption and other patterns in which individuals imitate others that are social norms that are not so good and things we want to change. So we need to think about these problems at multiple levels. Individuals exist within a social context. The social context constrains individual behavior, and on the other hand, the social context is defined by individual behaviors. It's a collective and dynamic phenomenon. As you see in the lower right, individuals through social norms may be led to do things like bind their feet or blow themselves up. Self-destructive behavior, because it's in a perceived to meet a common norm. And they can lead individuals to behaviors that are destructive to societies, like overconsumption. Now, human behaviors are obviously much more complicated than those of fish. They involve not just imitation, but responses to a variety of cues, including learning. And we build models, we make calculations about the future. Not clear those models do us much good, but we're able to look ahead and say what the consequences would be of our continued action. So fish presumably don't do that. And we have communication, we have language, so it's a very different sort of situation. Can we tease these apart? Can we model the dynamics of social norms and relate the scales from what individuals are doing to social groups and societies, and ultimately to understand how individual behaviors can be influenced to achieve the common good? Now, whenever I talk on this topic, people will properly, I think, latch onto this line here, because this involves making decisions. Somebody's making decisions about what the common good is. But that, after all, is what we do all the time in a democratic process, and I don't know any way around that. A literature's begun to develop on this topic. I won't talk to you about it today, but it builds on things like the theory of epidemics and the theory of population genetics. Pete Richardson here and Rob Boyd, Axelrod, many others have been working on this for many years, but the subject is rapidly developing now, and I think the real challenges have not been yet adequately dealt with in relating scales. Translating individual behavior into the groups and societies that form. How do those groups and societies form? How plastic are they? How do they change, and how do they change their practices? And how do these norms become rigidified into laws? So in conclusion, I began by talking about how the subject of ecology has evolved. It's built partnerships with many disciplines: mathematics, physics, engineering, molecular biology. And my argument is that the next great challenges lie at the interface with the social sciences. How do we value biological diversity? What are the collective consequences of individual actions? And what's the interplay between individual actions and norms? How do we construct an economic framework for decision making? Kenneth Arrow, who I mentioned at the beginning, has argued that conventional markets don't work, and they fail to protect the environment because they fail to incorporate social costs. If ecologists say that, it's tree hugging, but when an economist like Arrow says it, people listen, and it means that economists are eager for partnerships with ecologists and others in addressing these problems. Most fundamental, I think, most intriguing, is the issue of cooperation and of how to influence individual behaviors in the common good, because ultimately the solutions to these problems of the global commons are going to require the development of mechanisms of trust and cooperation. Trust, you understand, doesn't mean necessarily that you like the other person. It just means that you know how they're going to behave in a particular situation. And that's basically why the Montreal protocols work, because there are enough feedbacks in there that one trusts that they know how individuals are going to behave. Ultimately, we need to achieve that so that everybody can feel that they have something to gain from this collective behavior, and that we can achieve a sustainable future for our children, and that's my daughter, and our grandchildren, that's my grandson. So thank you very much. Jonathan.
So you had a few slides sort of distinguishing human behavior and human societies from animals and other types of groups. I'm wondering how much, in the people studying animals, how much you think there are laws of these interactions that apply across, say, all non-humans, and then within humans, how much what areas do you think those laws are going to extend to humans, like scalar interactions or
well, that in fact, as I indicated, is the fundamental question. My point of beginning is that many of the phenomena in human societies can be understood as being not a whole lot different from what goes on in animal groups, and resulting from little more than imitation. I don't see it as there being rules that apply all across the animal groups except humans and then humans. I think one has to look at this, at the emergence of these patterns as they change as you go across taxa. Now, human societies are more complicated, as I pointed out. There are a lot of other things that are going on. Some of the simplest things, and some of this, but almost anything I say is not going to be restricted to humans, is that humans don't just imitate, they persuade. We don't just communicate on a one-to-one basis. We have television, where political leaders and others can go on and spread information, and we don't hear back. It's an asymmetric interaction. Many of the models of imitation are symmetric. Individuals meet, and A can influence B, B influences A, but but we know there are power structures and how those emerge. This is what anthropologists, of course, have studied for a long period of time. So human societies are very different. So my point of beginning is, first of all, to observe that a lot of these phenomena can be understood as not a whole lot different than what's going on in those fish schools. But then to ask, how do we have to change them to understand what's going on in human societies? I was just telling Alan on the way over here that I came from a meeting at the Federal Reserve where the Fed is very interested in what they call systemic risk in banking systems, namely the question of whether a run on one bank will lead to runs on other banks and a collapse of the whole banking system, and how they can, I mean, that's not a whole lot more than imitation. So I don't know the answer to your question, but I think it is the fundamental research question. Gary.
I would have thought that if you look at species in community, they too have conflicting interests. They generally do not have the good of the community or the ecosystem in mind.
I'm sorry, what was it, if you looked at what?
At species in an ecosystem.
Yeah.
Species in the community, they too do not have the community's good or the ecosystem's good in mind. And yet, ecosystems do persist. And in fact, one can argue that those ecosystems that are most successful and most persistent are the ones in which the powerful create the good for the most. Have you gotten any insights from ecology and from the interaction among species as to how ecosystems are best organized to determine, quote, the common good, unquote, whatever that means?
Okay, so first of all, I agree with you that species don't have the ecosystem's interest in mind. In fact, species don't have the species' interest in mind because evolution's going on at a level much lower than the level of species. Where I disagree with you is the notion that that somehow they've come, in a sense of Adam Smith, to the optimal solution. I think that what we see is the ecosystem. So there's kind of an anthropic principle. We see ecosystems that have persisted over time. There are two main mechanisms by which, at the extremes, by which systems change. One is evolution through natural selection, basically, where you have entities producing copies of themselves and being selected based on their fitness. But also think of the metaphor of suppose you had a big old truck that you were driving down a bumpy road with a lot of stuff on it, and as it went down, stuff fell off. And either you reached a point where your truck stopped because critical things had fallen off, or you reached a point where the truck was still moving and stuff stopped falling off. So that's sort of a developmental process, and it is in fact the result of an adaptive evolutionary process taking place, if you will, at lower levels of organization. That's what we see in ecosystems. Ecosystems are self-organizing entities. They are not the product of natural selection. There's no way to measure whether they're better than than you could design an ecosystem because, for one thing, it's not clear what the objective function is. They are just things that grew, like Topsy. They are, until we can ask from a viewpoint of human services what's the best ecosystem. But from the ecosystem's point of view, it is just what it is. So in fact, we see systems that are like those trucks where all the other pieces have fallen off and therefore they become persistent. But it's not at all clear to me, in fact, it's fairly clear to me that the opposite is true, that these are not the best of all ecosystems that we could design if what we're interested in is their robustness to the sorts of perturbations that we're imposing on them now.
Well, I want to make it clear that I didn't mean optimality. I don't believe in optimality in biology, but what I wanted to say is that economies also have a major self-organizing aspect to them.
Absolutely. So that's why at the beginning I said economies and ecological systems are parallel. There are slight differences because you have Ben Bernanke, people may not know that name, but they knew Alan Greenspan, who was tinkering with the microscopic in response to macroscopic features. So in economic systems, you do have some regulators sitting on the system. But the first approximation, I do think that ecological systems and economic systems are similar. That's what they are, as I said at the beginning, complex adaptive systems made up of individual agents who are pursuing their own selfish agendas. And the patterns that you see at the end are the emergent properties of individual behaviors. They're not satisfying any design criteria at the macroscopic level. But that's not so much true for economic systems, as I said, where you do have some control on it. But I think the parallels are very strong, as you suggest. Yeah, Andy.
So, animal groups and or human social groups vary a lot in their social structure, in the degree to which power may be centralized in a few individuals versus many, and how linear is the dominance hierarchy, and just how connected different individuals are, how much substructure there is. Do you have a sense from your readings or your thinking about it on what kinds of social structures are more likely to result in cooperation?
Well, part of the question is what kind of social structures result from cooperation also, because the social structures are dynamic. And the emergence of cooperation and the emergence of social structure, that's a coevolutionary problem. And I think it's a very interesting problem, maybe one of the most fascinating questions in this area. You know, there's a lot of work, people like Duncan Watts and others on small world networks that have emerged. Most of that work, at least historically, has looked at, by the way, for those who don't know what a small world network is, it's a network in which every individual is connected by some criterion, like acting in a movie with Kevin Bacon, by some small chain of reactions to almost every other individual in the world, or at least in the largest cluster. That's a very simplistic version of it. So a lot of that, there's been a lot of work demonstrating how many of the webs that we see in the world are small world networks or scale-free networks or networks with other properties, and also what the consequences of that is, for example, for the transmission of disease. I chaired a committee for the NIH on influenza modeling for a while, and a lot of that, the work was concentrated on looking at the networks of contacts among individuals and what the characteristics of those networks were, and how it affected the probability of spread of disease, but another context of information, and another context of the robustness of those networks. And I have some thoughts about what sorts of networks lead to robustness, namely those that are compartmentalized, et cetera. But there hasn't been a lot of work on how those networks form. That's just starting. And I think one can ask the question that you asked, but really should ask it coupled with, and how do those patterns of cooperation lead to particular sorts of network structures? And are those network structures the ones that would most facilitate cooperation? So I've thought about that problem a lot. I don't have a good answer, but I do want to emphasize this notion of that network as being dynamic. Anthropologists have been interested also for a long time in how the hierarchical structures within societies emerge. But I'll just leave it at that. Well, that's really an interesting question. My expertise on that is certainly no greater than yours. I have my own thoughts that probably I shouldn't. But one of the things, and I've actually, I mean, you could ask the same thing about willingness to impose punishments, and people have done that, those experiments. In terms of thinking about cultures, not in terms of ethnic background and things of that sort. So this is well outside my area, but these are obviously crucial questions to ask, and there are questions that people have done experiments on. Different cultures have different traditions of cooperation, of charity, of communal responsibility, but not my area of expertise.
So it seems that you're taking a view of the world as sort of being highly organized and giving no role to the random or big rare events that, for all intents and purposes, and timescales we're interested in may as well be random. And so, do you think there are classes of problems that we're dealing with here, though, that are subject enough to catastrophic rare events that the self-organization that you're portraying may actually be less relevant?
Well, I don't take a view of the world as being highly organized. I'm not even sure how I would measure that. But in terms of the second half of your question, I certainly think that catastrophes and surprises are occurring all the time, causing breakdowns of parts of the system and the ability of systems to reorganize. That because of that, and this is did I do that? I think that's a hint. Yeah, sorry. I don't need it. I don't need it really. Because of that, where is I going? The systems that are most persistent. I'm trying to phrase this in a way that also addresses Gary's question before. The systems that are most persistent are those that have the capacity to adapt over time and that maintain features like heterogeneity and diversity at lower levels, to have the components in them that allow them to adapt. So I'm not sure what I said that you were interpreting as my thinking that the world is highly organized, but I certainly think that the surprises and catastrophes and the ability to deal with those on different scales are crucial features of the organization of these systems. So with that nod, I'll take. Yeah.
In your model for your swarms,
Yeah.
you talk about leaders there, and how society evolves depends on how strong leaders are, to some extent also. And you talk about how fast the system goes in the direction that leaders want. Did you also study what fraction of leaders are important in terms of getting where they want to go? What happens if you have different leaders?
Yeah, we did, and I showed you one slide that had the number of leaders on the bottom. And so in that particular case, they were all trying to go the same place. So all we were measuring there is how fast they got to that point. What we're doing now is putting this in an adaptive framework and saying, well, what are the best rules for you to evolve? Suppose let's deal with the animal group, and let's suppose the measure of success is how fast you acquire nutrients or resources, and those resources are being presented stochastically, spatially. You could ask the question from the viewpoint of the whole group, if this were a collective foraging unit, how it would maximize its resource intake, or you could simply view this as we do as a game theoretic problem. And you can either follow your own information or follow your neighbors. If everybody followed their own information, they would be collecting nutrients, but not at the optimal level. If everybody simply followed everybody else, they wouldn't acquire any resources. And this is a game theoretic situation. So we're beginning to investigate what, I don't know if that addresses your question, what the optimal behavior is, or what the evolutionarily stable behavior is, if you will, and whether you maintain multiple behaviors. Yeah, okay.
Before we thank Simon again, let me remind everyone there'll be another talk tomorrow at 12:10 in the ARC Ballroom A on the evolution of ecosystem patterns.
That'll be a more technical.
just in problems of the commons and overuse of resources.